So we spent a lot of time in this chapter talking about the ideal gas law, right? PV equals nRT. And this is how we solved for any of these four variables of a gas if we had the other three. So if we had pressure, volume, and number of moles, we could figure out the temperature of the gas because we have this ideal gas law equation with this constant. And the amazing thing about this was that we said it's a very good approximation and it doesn't depend upon the identity of the gas. We actually don't need to even know what the gas is. Is it water vapor? Is it nitrogen? Is it hydrogen? It doesn't matter. The ideal gas law is still very, very accurate. However, now what we're going to do in this video is talk about how the ideal gas law can fail and what is an even better equation that we can use to describe the properties of gases, okay? And so at STP, right, 0 degrees Celsius and 1 atmosphere of pressure, the ideal gas law, if you plug in those values for 1 mole of gas, the volume will be 22.41 liters. That's shown by this blue bar here. That's what the ideal gas law states. And you can see for a variety of different gases, okay, it's pretty accurate, but it's not 100% accurate. It's actually not 22.41. Interestingly, for helium, it is equal to, it is accurate, at least to 2 decimal points. And we'll talk about why helium is the most accurate one of these. But you can see there is some deviation. Chlorine is particularly bad. Okay, so in actuality, no gas is ideal. And so we call that the opposite of an ideal gas is a real gas. And so we need to improve our ideal gas law equation. And so what are the assumptions that we talked about on the kinetic molecular theory video that need to be fixed, okay? Because those assumptions are giving rise to the inaccuracy in this PV equals nRT ideal gas law equation. So that kinetic molecular theory, which forms the basis of this ideal gas law PV equals nRT equation, assumes that gas particles themselves don't have volume. Now, of course, that's not true. All particles have volume. Just like all matter has volume. That's part of the definition of what matter is. Now, the ideal gas law, of course, takes into account the volume of the gas, but in a container, but it assumes the particles themselves have 0 volume. And that's not true. So we're going to fix that assumption. The other part of this is that the ideal gas law assumes that gas particles are not attracted to one another, or that these attractions are basically negligible. And we know that's not true because all gases, including helium, can be liquefied. And liquids, the fact that any gas can be liquefied tells you there are intermolecular forces. There's attractions between those gas particles that can become strong enough at a low enough temperature to liquefy that gas. Helium has the lowest boiling point of about 4 Kelvin of all the gases, but it still can be liquefied. And so the equation that fixes these things is called the van der Waals equation, okay? And van der Waals received one of the earlier Nobel Prizes for this work and also work on intermolecular forces. So he's the intermolecular force scientist, okay? And this is the equation. It has a p-type term, a v-type term. They're multiplied by each other still, and it equals nRT. So it looks very similar to the ideal gas law, but it's just a little bit more complicated. We have this, let's go over this volume correction factor first. This one's a little bit easier to understand. This is basically saying we're going to have some constant B, okay? And this constant B is going to be bigger for bigger molecules, gas molecules, and it's going to be smaller for smaller gas molecules. And we're going to times it by the number of moles of gas. And we're subtracting it off. So this is telling us that, hey, the actual volume that we care about is the volume of our container minus the volume of the particles, of the gas particles. And so if you have a lot of gas particles or you have very big gas particles, this term is going to become bigger and that correction factor is going to become bigger. And then there's this attraction correction factor. And this attraction correction factor turns out to be related to the square, okay? But it's related to the density also, the square of the density. So this is N over V, right? And this makes sense, right? So number of moles divided by volume. That's the density of the gas, the molar density of the gas. If you have a greater density, this value better go up. And again, because you're gonna have more chances for gas molecules to interact at higher density, and therefore you need a bigger correction factor, okay? And there's this term A here, that's also constant, and that correction factor is going to vary depending upon what the identity of the molecule is, how strong are those intermolecular forces, okay? And that's sort of the basics behind this van der Waals equation. And so what was shown here is the value of PV over nRT, okay, on the y-axis. And that value should be equal to 1 for an ideal gas because PV equals to nRT. So PV divided by nRT equals 1. That's this pink line. Just hanging out at 1 because at all pressures, okay, the x-axis here, the ideal gas law says that, hey, it's going to be equal to 1. But what we can see is that actually that's not true for real gases. And we get bigger and bigger deviations in general from the ideal 1 value as we increase the pressure. Because again, we're jamming these gas particles together. And so then we have more chances for attractions, and the volume component of the gas particles takes up a higher fraction of the overall volume container as we get to smaller and smaller volumes, higher and higher pressures. And you can see for helium, we call it a volume dominated gas, meaning that basically it's just a straight line here, which makes sense. This is a linear correction factor here. And so it makes sense that we should have a straight line for this volume dominated gas. It means that helium isn't interacting with itself very much. And instead, the only correction factor I have to do is this volume portion of the van der Waals equation. You can see here we have values that are greater than 1.3. Now, for the ones with these curves, that's coming from the squared portion of this function. And so these are attraction dominated. And you can see for water, it's really attraction dominated. Water has very strong intermolecular forces because of hydrogen bonding. And so you get this very strong quadratic relationship here, okay? Then you have ones in between like xenon that are both volume dominated and attraction dominated. But yes, helium is a very, very small inert gas, the most inert atom that there is. And so it really doesn't have any or pretty low component of this attraction quadratic term, okay, right here. All right, so what you can do is then you can solve using this equation, the van der Waals equation, and get the actual values in here, okay? And so here's a problem. I'm not actually going to go through it, but it's fairly straightforward. It's mostly just plugging things in. I'll talk about how we will do that. Using the van der Waals equation constants to the right, you're always going to be given these. At what temperature would 1 mole of Cl2 have a volume of 22.4 liters and 1 atmosphere? So we plug in 22.4 liters for volume here and here now. 1 atmosphere would go in for P, and then we have 1 mole, so N here and here would be 1 and there. And then we have A and B values that we plug in, they're given to us here. The ideal gas constant is still 0.08206 liters, atmospheres, moles, Kelvin, still the same thing. And then we plug all that in and then we solve for T. And solving for T is straightforward. If you need to solve for V, that can be quite complicated. It ends up being a cubic expression here. So you might need some equation solver to do that online. But you know, there's those variations on a theme. It's just solving some algebra. Here's just showing you what that value ends up being. So if you do that for chlorine, you get a value of 2.8 degrees C. And you can see, just as with the pressures and what we're talking about, helium and neon, noble gases, they're pretty close. Nitrogen, a pretty inert gas, not a lot of attractions, pretty close. Now, why is helium, worse than neon? You might wonder that because helium is so tiny. Well, neon has some attraction component to it and some volume component, and those effects cancel each other out, and it just happens to be that it gets you closer to 0 degrees C, which is what the ideal gas law would predict. So that's just a case where the ideal gas law fortuitously happens to be more accurate, but really that's just because there's two competing factors working in opposite directions.